So last up we have Bryon Lewis, who is, in general, his presentations every year are always interesting, and he always brings an interesting perspective, a little different, a little fun. So there's a reason he's last. He's a fun guy to listen to. So I'm glad to welcome to the stage yet again, Bryon.
Thanks, Dale. Thank you. It's always an honor to be here. Here's a way to think about data, especially large data, that can help make complicated problems easier to solve sometimes. And I love projection methods because they're so familiar. We all have lived with projections all of our lives, and we all have a deep, visually intuitive understanding of them. Our culture has used projections for millennia quite profitably, and we continue to do so even mathematically today. And they're even a big part of our popular culture today. So projections are all around us. So here's the central, really the central idea of this talk. Even though the kid's shadow in this picture is living in a lower dimensional space, it still retains a certain essential kid-like quality to it. We can recognize it as being different, for example, from the shadow of the tree behind him. And the main idea that I want to get across is that we might ask a question about the real world, the whole space, and then try to answer that question using only the shadows and the projections, in the hope that because it's a smaller dimensional space, it'll be much easier to solve. Now, of course, the point of view, the perspective that we take on those projections is going to make a huge difference in our ability to answer questions. For example, here's a group of 3 guys standing around, and we can see that they're different. They've got different heights and so forth. But if we change our point of view and look at their silhouettes from a different angle, we get a lot more information about them. The guy on the right, maybe he needs to get a little bit more exercise. And the guy on the other side, I'm not sure is even a guy, right? It's probably a girl. The purse is a dead giveaway. Where's Jeff? So analogous, just like the real world, we can do the same thing with our data. So here's a depiction of 3 points in 2-dimensional space, and I'm shining a light through them onto a 1-dimensional projection screen up at the top. And this is a pretty crappy projection because, as we can see in the real world, those points are really far apart, some of them, but in the projected space, they all look kind of like the same distance apart from each other. It's a very bad projection that doesn't give us much information. But just like with the silhouettes of people, we can rotate that lamp and projection screen around our data, keeping a right angle between the light and the screen, and until we get to a situation where we get a lot more information about the points in the projected space. Like from this viewpoint, we almost exactly reproduce very closely reproduce the actual distances between the points in the real world. And we can say, for example, that bracket there, that the purple and pink point are at least that far apart from each other. And indeed, they're only a little bit farther apart in the real world. The viewpoint that we take on the data are going to be essential into our ability to answer questions about them in a projected space. Something I have to say is a lot of people, when they think about projections, they think about approximations. Like I just mentioned, that we're kind of estimating distances between points in a projection. But most of the time, I don't think that way. For example, imagine a question about these points where instead of, let's say you were interested in finding all pairs of points that were close together within some threshold. Well, we can answer that question exactly in the projected space by finding points whose estimated distance exceeds that threshold, pruning them out of our data set, and then focusing on the points that are left behind. It seems like it's an embarrassingly obvious kind of algorithm that I was working on publishing last year, amazingly, even though it's so trivial, along with Mike Kane, who's here, and Jim Buglama at the University of Rhode Island. And we have an R package and a paper that talks about this kind of thing for distances and correlations and stuff like that. And the title of this talk comes from that algorithm because in a way it's kind of a long-distance cousin from an iterative cousin of these divide and conquer algorithms. What the T-core algorithm does is it takes a set of vectors, projects them to a 1-dimensional space, prunes out vectors that exceed some sort of distance or correlation threshold, and then augments the subspace size iteratively to improve its pruning capacity until a sufficiently tiny number of points are left to evaluate using a more expensive approach. And here's an example that's described in a vignette in the package of a kind of a small, modest-sized 1,000 by 20,000 matrix, in which you might ask a question, show me all pairs of columns in this matrix with a Pearson's correlation coefficient greater than 0.99, a kind of a thresholded correlation matrix problem. A brute force implementation of that, to solve that question, needs about 200 gigaflops to solve it, and that's an efficient brute force implementation. But for the matrix described in the vignette, the T-core algorithms solves exactly the same problem using only 1 gigaflop. And that's kind of the idea behind projection methods. Sometimes, if we get the right point of view and formulate our questions correctly, we can solve an equivalent problem in a projected space with a lot less effort. And I've already extended this algorithm to data sets with millions of columns, and it's very easy to do that and runs very efficiently. So I keep saying that this point of view and the perspective matters, and so we need to think about what types of projections to use and into which spaces to project to. And I prefer to use Krylov subspaces. These are kind of the spaces that I've worked on all of my life. And here are a couple of examples of how Krylov subspaces can be generated for an operator X and a vector beta. If you've heard of algorithms like Lanczos or partial least squares or use such algorithms, you've already used Krylov subspaces. And most of the work that I do fundamentally relies on Krylov subspaces. So I'll just kind of go through a bunch of applications that are seemingly very different, but that all use Krylov subspace projection methods under the hood to efficiently solve complicated problems. These aren't all my applications. They're just a mixture of things that over the years I've encountered. I was happy to hear Dave Demer's talk earlier today mentioning absorption ratio methods, which are a principal component like projection of financial data into a lower dimensional space. And I've worked for many years on kind of a state-of-the-art algorithm for doing that on CRAN called IRLBA, and it's very efficient for solving problems like that at extremely large scales. So that's a question where we really are looking for an approximation. We simply want to shrink our data down and focus on an information-rich subspace inside of our data. Other folks use that same algorithm to project data into lower dimensional subspaces and then apply clustering methods like k-means or other clustering algorithms there with kernels or without kernels even. So that's another very interesting application of projection methods that can help you make sense of, are my data grouped or not. A really interesting algorithm that came out of UNC about a decade ago it talks about bi-clustering data, which is where you permute the columns and rows of a matrix to group similar rows and similar columns together in a kind of a checkerboard pattern. And there are many algorithms that do this kind of thing. In R, there's a bi-clustering package called biclust, and there was a package, a modular package for that by Kaiser and Sill that implemented this UNC algorithm of Lee and Marin and Shen. And it was a really neat application, but I talked to them when I realized a few years ago that they could benefit from solving exactly the same problem that they were solving, but doing it using these projection methods. And so they ran with it and made an update for their package, and here's a result from them of their package. They were able to dramatically improve the performance of their package and solve precisely the same problems. In this example of a 1,000 by 10,000 matrix for biclustering, the run time of their R package went from 3,500 seconds on my laptop to 20 seconds. And it was just solving exactly the same problem, just using a subspace method. Maybe your data represent some sort of a network, maybe an adjacency network or something like that, and you might be interested in finding most central nodes of a network, or perhaps the paths through which data flow most freely in the network. I mean, this is a common thing in finance. Mike and I worked for DARPA on kind of Bitcoin analysis like this years ago. And here's actually an application to Bitcoin of just a subset, kind of a 1,000 by 1,000 subset of the Bitcoin transaction graph, which is a directed graph, and we applied the Kleinberg hub authority kind of, it's just a way, it's a fancy algorithm from Kleinberg to find central nodes in a directed network. And it's a really nice algorithm, but it's fairly complicated and expensive to solve. So here's a slide from a talk that I gave at this conference about 5 years ago or so, where we applied these Krylov subspace methods to solve that problem. And it's a comparison with the kind of default matrix exponential in R. And you can see we get the same results. The numbers are the same, but the runtime went from, again, on my Chromebook, from 150 seconds to half a second or so. Again, the same problem was being solved. And really, I just recently encountered a paper by Candies and others for the matrix completion problem, which is kind of was made famous by Netflix and Amazon for recommending products and movies to people. And this is where you've got a matrix of data, but a lot of the values are missing, and you would like to impute them, subject to a constraint on the rank of the matrix, right? So here's the formal matrix completion problem. You find a minimum rank imputed matrix that matches your given matrix on the nodes that you have available, the non-missing nodes. This is an NP-hard problem. It's not tractable to solve. But Candies very cleverly found, in some sense, the closest convex problem to that. And that star norm is the nuclear norm. It's kind of a fancy norm for a matrix. It's the sum of the singular values of the matrix. There, Dirk, I said singular values, so we're, you thought I would get through without saying it, but I said it. Yeah, so, and that solves a really close problem, but that is tractable. And I looked at their lovely paper and realized that it's self-evident from their paper that it uses a projection method, but they didn't think about using these Krylov methods to do that. And so I put a very crude prototype code up on this page that has a really cheesy prototype implementation of that. If somebody wants to play with it, it's kind of neat. And then finally, the last application I'll talk about of how these methods can be really, really neat is the one I'm by far the most excited about. And this is what Michael Wayland was talking about earlier today, of picking interesting features out of data, right? So we're interested in finding the most important or somehow the most interesting columns of a matrix in a model or some other setting. And because that, as Michael described, that's also a computationally intractable problem, the most common approach by far, and a hugely successful one, is to use the lasso. And here's the problem stated kind of semi-formally. But what's so exciting is that some colleagues of mine last year formulated this problem as a projection method problem using Krylov subspaces in a very general form, which will allow us to not only solve the lasso problem, which we can do now, but also solve something much closer to the optimal subset selection algorithm that Wayland was talking about earlier, in a way that we can compute, actually, using these methods. So that's work that's ongoing, that Mike and I and Omar Delacruz and Lothar Reichel and many others are going to be working on hard this summer. Hopefully by the fall we'll have some nice new R packages and papers for that. Now, I know it seemed like a lot of different applications, but I want to convey that they all are under the hood exactly the same. It's like the kid's shadow. We're just looking at shadows of data, which is a smaller space, scrunching our problem down into that space and trying to find a way to solve our problem there, which is hopefully much, much easier to do. So effectively, projection methods turn big data problems into just data problems. And here's a link to these slides and also some code snippets. I have some prototype codes up there that aren't going to make it into R packages that you can play around with. But I want to finish. So I was very fortunate to know Diethelm Wirtz, and he introduced me to everyone in this conference. And I owe him a debt of gratitude for introducing me to all these friends and this wonderful community of people. I think Jeff will have more to say about that.
Wow, it's the end of the day. So I actually would be remiss to end this year without a comment on Diethelm Wirtz. To many of us, Diethelm is the father of finance with R, so the creator of R metrics. Our metrics introduced a lot of people to R, including myself. The biggest contribution was far larger than those 20 packages or so that he created. It was really this community. Many of the people in this room were referenced on slides or in talks, were really first met each other over a handful of summers near Interlaken at DTLM's Pioneering Conference. If I just look around the room or on the slides, I mean, Iakis, Bout, Lewis, Bryon, Zivit, Peterson, Pfaff, Alexios, Matt Dowell, Mike Kane, Peter Carl, all of them we met there. Those days and nights really were kind of the beginning of these friendships that Bryon alluded to have really lasted and truly have forever altered the way we use R, like all of us use R. It's fairly amazing. As Bryon also said, we lost DTLM suddenly last summer, and with that, a lot of us lost a mentor and friend. What we didn't lose, though, and the thing that I think we get to keep building here, is this community that he started. And we have, like I say, right here. I just wanted to end with thanks for being here and being part of the thing that DTLM started many, many years ago. Thanks.
So this is sort of the end of the conference. There's a few words that I'll say. Normally every year I get up here and I say, look, there's a reason that we have you here. There's a reason that universities exist, and that it's bringing all of this knowledge together, and that's why we're glad to host the conference. For a number of years, I've sort of inflicted a lot of this stuff on my students, in part because I have a lot of frustration with the investment texts that are out there, that they're not rigorous. And so I promised Jeff that some of you have been trading around the microstructure intro slides and trying to get the code that I put out there early on in the first conference. That stuff's going to be out there. I'm actually going to write up as an investments text, an actual investments text that uses R and has theoretical models in every part. So when we'll see what asset classes really look like. So if you're interested, send me an email and you can see if bounce a little bit of it off you. But that's the whole reason, like Jeff talked about community, that's why we come here to UIC. Unfortunately, this is my last year at UIC, but that doesn't mean that we're not continuing with this. So maybe somebody else next year will be up here saying thank you for coming to UIC, but it won't be me. Lots of change, but lots of good stuff. So with that, we should head to the place where this all first started, where we first had a night where we wondered if anyone would be interested in talking about the things you can do with R, and that's to Jack's Tap. So if you head down the escalators, and when you get down at the bottom of the escalators, take a right and go through those revolving doors, and then take another right, and that'll point you toward Jack's. So thank you guys so much for coming and for making this a wonderful time.